In this video, we're going to take a look at example number 2, and we're going to continue to use Taylor's theorem to answer some questions. So I want to use Taylor's inequality here to determine a value of n, remember that's a degree of a polynomial, that I could use to approximate e, notice that's e to the first power, accurately to 2 decimal places. So if I was to take a look at what I actually am interested in doing here, we know that what we're interested in trying to determine right now, if I take a look back at the previous picture, is again, how big of a polynomial do I need? So that way when I plug 1 into it, that gap is kind of small enough that I know that the first 2 decimal places are going to be guaranteed to be accurate. So I'm going to go ahead and start by stating the following. So I'll say, we know that if we want to estimate two decimal places of e accurately, then I'll say it must be true that when I go ahead and I measure my remainder at that specified value of n, at the x-coordinate of 1, that remainder has to be smaller than something. Now here's what it would need to be smaller than. I would need this remainder, I'll just have it strictly be less than, but I need this remainder to kind of have the appropriate amount of error. I need it to have 0 error in the ones digit, 0 error in the tenths digit, 0 error in the hundredths digit, so that all these places are perfect, and then I can technically select any amount of error that I want for the last digit. Now for the sake of making computations fairly easy, I'm going to put a 5 here, but you could really put any number in the world that you want. I just like a 5 because you'll see that it makes my number calculations fairly simple. So here's what I'm going to go ahead and do. If this is what I want to be true, then I can go ahead and I can start stating this. I already know that by Taylor's theorem, I know that if I was to actually calculate this, this would be less than or equal to, and we already saw that this could be, oops, excuse me, not e up there. We saw in the last question, you can even see it written on the page up above, that we were able to kind of, oops, express it as follows. We could have that as 3 over n plus 1 factorial. I'm not sure what n to choose yet. And then I can still do 1 minus 0 and then n plus 1 factorial. Now if I simplify that down, I still get 3 over n plus 1 factorial. Okay, because this over here is just going to be 1 to a power, and that's still just going to be 1. So this is what I know the remainder is bounded by. I just have to choose a value of n. But if I want this above statement to be true all the way over here, then I can start to think about how I can make that happen. I can go ahead and state that if I want my remainder overall to be less than this 0.005, I can then say that we want this 3 over n plus 1 factorial to be less than 0.005. Notice, if this is less than 0.005, then certainly my remainder is less than 0.005. And what I have here is a nice little inequality that I can attempt to solve. So let's see, if I was to try to go ahead and solve this, this would be the same as 3 is less than 0.005 n plus 1 factorial. If I divide both sides by the 0.005, I'm going to get a nice clean value of, I think, 600. And here's where I might have to start doing some guessing and checking. I'm curious right now, what would be a value of n that could make the right side bigger than what's on the left side. So like clearly a value of 1 isn't going to cut it, because 2 factorial is not bigger than 600. But what about like if I plugged in a 3 or a 4 or a 5? Well, I just like to think about the overall factorial. So you might even be able to check this on your own. 5 factorial overall. Would 5 factorial work? Well, if you check 5 factorial on your calculator, you see you get like 120. It's not big enough. What about 6 factorial? Well, 6 factorial would definitely be 720. So that would definitely work. So what this would imply is that I would need n plus 1 to be a 6 total. That would mean I would need n to be kind of greater than or equal to a 5, right? If it was a 5, it works. If it's anything bigger than a 5, certainly it also works. So this seems here to be a perfectly reasonable way to solve this inequality that I have. So with that, now I can see that we can use a degree 5 polynomial to estimate e to the first power with 2 decimal places of accuracy. Right? That'll do it. And the best part is that we actually already defined a long time ago a series that would actually model this e to the x function. You might recall, and I'll just put it down here, that e to the x we said was going to be modeled by the following polynomial. It was going to be modeled by, I think it was x to the n over n factorial. N goes from 0 to infinity. This was the polynomial we came up with, and you could go back and double check that you could build a polynomial of this exact shape. But notice that if I plug in an x equals 1, then that means that the polynomial that models my e to the first power is going to look like this. I just replaced x with a 1. And once I have this, what we've said is that if you then want to estimate what e to the first power is, I can then say that to get 2 decimal places of accuracy, I can just write out, see, 1 over 0 factorial is 1, 1 over 1 factorial is 1. Notice I'm going to do 1 over 2 factorial, then 1 over 3 factorial, then 1 over 4 factorial, and then finally 1 over 5 factorial. Oops, except I stopped writing the factorials. 4 factorial is supposed to be 24, and 5 factorial is 120. I believe that if you were to add all of these values together, you would get something that is actually roughly 2.71, which is exactly what e is to 2 decimal places. Now you might get some other decimal places on here, which is totally fine, but we'll notice that the first 2 are perfectly accurate. So what this Taylor's theorem is allowing us to do is something unbelievable. It's allowing us, for the first time in mathematical history, allowing us to approximate unbelievably difficult values to kind of as much accuracy as we want. I mean, couldn't I imagine changing this question here to saying instead of accurate to 2 places, I want it accurate to 200 places? Well, sure. I might have to go ahead and rework a little bit of maybe solving this inequality. I'm definitely going to have to change the decimal that I want to be less than, but I can go ahead then and figure out how many terms of this power series I need to, or the series, I guess, that I need to add up in order to be able to approximate this value of e as accurately as I want. That's a really powerful idea. Okay. In the next video, we'll take a look at an extremely surprising result with examples 3 and 4.